This is problem 2-51. It's on page 101. A fan is used to accelerate quiescent air, in other words, air that is still, to a velocity of 8 meters per second at a rate of 9 cubic meters per second. Determine the minimum power that must be supplied to the fan. Take the density of air to be 1.18 kilograms per cubic meter. Okay, so here's the fan. We're putting power into the fan. And what the fan does is take air that's still and turn it into air that's flowing. Now it does this at a rate of 9 cubic meters per second. That's the volumetric flow rate. And the final velocity is 8 meters per second. The initial velocity is 0. The density of the air is constant at 1.18 kilograms per cubic meter. So we've got all that written down. Now let's calculate this and see what we get. All right. Well, how will we quantify this? How will we take care of it? Well, remember, if you look at the back of the chapter in the summary, page 97, you'll notice there's an equation that allows you to quantify the amount of specific energy that a fluid has. Air is just acting as a fluid. Don't be confused. In this context, when we say fluid, fluid can mean a gas or a liquid. It doesn't necessarily mean something that's liquid. In your everyday language, you probably just use fluid for liquids. But in engineering terms, a fluid is a liquid or a gas. So pressure over density is part of the equation, plus V squared, over 2, which represents kinetic energy from velocity, plus GZ. Now, we don't know anything about the elevation change across the fan of the air, so we can't say anything about how the potential energy of the air changes. The pressure before and after the fan are the same too, because this is all just exposed to atmospheric pressure. So the only form of energy that we're going to track in this problem is the kinetic energy. And so if we were to write something like an energy balance for this, so we take our system, it'll be something like this. How much power do we have to put into this system to get this to work? Well, all of the power that goes in, ideally, will accelerate the fluid. And so we'll basically give energy to the fluid. So that would be the energy of state 2 less the energy of state 1 times the mass flow rate of that air. Okay? So basically what we're saying here is each, what units are we in? We're in metric. So each kilogram of air that comes into this system has kinetic energy. And each kilogram of air that leaves the system also has kinetic energy. And of course they're going to be opposite, or they're going to be very different. Now I pointed to the wrong ones. This is what's coming in and that's the one that's 0. This is the one leaving. All right, so let's write this down. Now we need the mass flow rate, but all we have is the volumetric flow rate. So we'll have to expand the mass flow rate into density times volumetric flow rate. And then E2, all that will be left is V2. So there will only be kinetic energy as far as we're concerned at the exit. Okay, so now what? Well, I think now we plug in. Density is 1.18 kilograms per cubic meter. The volumetric flow rate was 9 cubic meters per second. So notice that gives us the mass flow rate in kilograms per second as we expected. The velocity at the exit is 8 meters per second. That has to be squared. We have to divide by 2. Okay? So 64 over 2 is 32. We need 32 multiplied by 9 and multiplied by 1.18. So let's see what we get. 1.18 times 9 times 32 is 339.84. What units do we have? Well, let's see. We've got kilograms per second multiplied by meters squared per second squared. Now, you'll get used to seeing this, but let me pull some things out. Kilogram meter per second squared. Notice I've excluded one of the meters. A kilogram meter per second squared is just a newton. So this is just Newton meter per second. A Newton meter is a joule, and a joule per second is a watt. So essentially, what we have here in these units is simply a watt. Okay. So there's the minimum amount of power required. Now you'll notice your author gave you an answer of 340 watts. He just rounded off, which is reasonable, of course, but there's our answer. Okay. They asked for anything else? Nope, that was it, so we're done.